Hello class, and welcome back to our study of frequency response, which is chapter 9 in our textbook. So in my last two recordings, the first was the lecture and another was the problems, we looked at these two topics. 9.0, which is basically just a review of previous material that we have covered on frequency response, filters, Bode plots, and so on. So we did a little bit of that last time, and then we also looked at the low frequency response of the CS&C amplifiers, the MOSFET and the BJT on the low frequency side, where we noticed, we were told that the capacitances that were important were the external capacitances, the coupling capacitance, the bypass capacitance. Those determined your low frequency response, meaning what is the cutoff frequency below which the amplifier's response is not usable, meaning it becomes too low, the gain is not stable and it's too low, and so on. But above the cutoff frequency, above the lower cutoff frequency, we find that the amplifier is useful. So we studied all that, and we also found some formulas to determine the size of the capacitors, the coupling capacitor and the bypass, depending on where you want your cutoff frequency to lie, right? Your minus 3 dB frequency, if it has to be 100 hertz, and you know the transistor parameters, you can say, okay, the coupling capacitor has to have, be so many nanofarads or picofarads or whatever. Similarly, when we were given the size of the coupling capacitors, we are able to then say what is the cutoff frequency on the lower side. So those were some of the things we learned. In this recording, this and the next one, we are now concerned with the high frequency side, right? And so we will look at topics 9.2 and 9.3. Okay. All right. So let me move ahead to slide 31. Yeah, slide 31 is where we start section 9.2, and let me see if I can amplify it. Yeah, so you can amplify. All right, so you can see better. So here we start to look at the internal capacitive effects and the high frequency of model of the MOSFET and the BJT. So what that means is, at the high frequency, it is not the outside capacitors that you connect in the circuit for coupling and bypass, but as the MOSFET is being fabricated, as it is being assembled in the factory, because of the internal construction of the MOSFET or the BJT, some capacitances creep in. They exist in the device. Whether it's a single MOSFET or it's an integrated circuit with many MOSFETs, either way, because of the internal construction of the MOSFET or the BJT, certain internal capacitances occur or come into existence, and they tell you what your high frequency cutoff will be. So, how many gigahertz or how many megahertz on the high frequency. On the low frequency, you're talking, 100 hertz, etc., right? Such numbers. On the high frequency, you're talking gigahertz and megahertz. So what will be your high frequency cutoff for a given transistor, whether it's a MOSFET or a BJT, is the question that we are most interested in. So let's see, let's look at the pictures and then we can look at the notes here. So this is a photograph or an image from previously where we use this to understand how the MOSFET works, right? And first we are talking the MOSFET, then we look at the BJT. So we know that the MOSFET construction looks like this. An NMOS MOSFET is what you see here. There is a P-type substrate in blue. Then there are two wells. There is an N-type well for source and an N-type well for drain. And the gate is in the middle and a thin channel is created, right, when you apply a voltage. Actually, that channel looks like this, not so much as the voltage goes higher, and then it's pinched off at this end. But anyway, this basic construction, and then there's this material, this insulation material, the silicon dioxide, that exists between the gate electrode. The black material here points to an electrode that you attach to the N-type or the P-type material to get your terminal, right? The pin that connects the outside circuit to this N material is that black thing. So there is a black electrode here, there's a black electrode for the gate, and there's a black electrode for the drain. And then you get this induced channel and electrons start to flow in this direction, right? ID is the current, it comes in like this from the positive terminal and goes out like this, right? Okay, so this we know. So now what is shown in this drawing is some new capacitors, right? So there are four capacitors that you see here: CGS, CSB, CGD, and CDB. So what are all these capacitors? And then you see a little bit of a length being shown here, LOV, right? So what are all this? This is all new stuff. So let's see what the notes say. First of all, the gain fall off at high frequencies is caused by the capacitive effects internal to the transistors. Two types of internal capacitances exist in the MOSFET: the gate capacitive effect and the source body and drain body junction capacitances. So there are two types. The first type gives you three individual capacitances, and the second type gives you two individual capacitances. So what is the gate capacitive effect? The gate electrode, which is this electrode, forms a parallel plate capacitor with the channel. So there is a channel here and there is a gate here, and in between is a dielectric, right? These two are conducting. The dielectric is an insulator, hence a capacitance is formed. You can easily understand that. So the gate electrode or the polysilicon forms a parallel plate capacitor with the channel, and the oxide layer in the middle serves as the capacitor dielectric. This capacitance per unit area is COX. Now COX we have seen enough times previously in the formulas, so I'm not going to worry too much that you don't know this, you already know this. Now there can be gate to source. So gate to source, there is a capacitance as shown here, gate to source. Gate to drain, so this side is gate to drain as shown here, and then gate to body, which unfortunately is not shown, but similarly you can draw one capacitance between this gate and this p-type body, which is also called the substrate, right? So those are because of the gate forming a capacitance because of the dielectric that exists in the middle, the insulation in the middle. The other type of major capacitance is the source body and drain body junction capacitances. So there is the source and the body, right? That's the CSB. Then there is the drain and the body, and that's CDB. These are the capacitances of the reverse biased PN junction formed by the N-type source region and the P-type substrate, and by the N-type drain region and the substrate. And both these are reverse biased in the sense that, as you can see, this N-type has a positive connected to it, and we also know that the body is connected to a negative terminal in ICs in particularly. So because of the reverse bias on these two terminals, we get capacitance, and those two capacitances are shown as CSB and CDB. Okay. Alright, so that is your first introduction to the internal capacitances. Now let's look at a little more at each one of them. Next slide shows you again the same picture from the previous slide of the internal capacitances, but I also brought in the old picture, old image, to show you a couple of things. So we talked about two types of capacitances, right? Because of the gate and because of the reverse biased body. So let's look at number one first. Again, this has three, right? It has CGS, GD, and GB, right? So that was the three that we were shown in the previous slide. Here though, what we see is CGS and CGD, you have to separate them into the triode region capacitance, the saturation region capacitance, and the cutoff region capacitance. So based on the physics of all this, which we are not going into, and it's not too detailed in the textbook either, but just, let's assume that the physicists and the chemical guys who studied all this material, they are giving us the capacitance, so we just accept it. So the formula for GS or GD, gate to source or gate to drain, is half width times length times COX. Now we know COX, like I said, we have seen it previously. The new factors are the width and the length. So this is the width and this is the length. We have seen this before, right? W by L, etc. we have used in formulas. So here the W by L is not used, W and L come in separately, and these are generally in micrometers, right? Now in the triode region, they are equal. In the saturation region, gate to source has this formula, gate to drain is 0. Cutoff, they are both 0, the gate to source and gate to drain. And the third one, GB, gate to body, has this formula. Now the gate to body is not shown here in triode and saturation, so I assume it's 0. So you have all these formulas to tell you what exactly these three gate effect capacitances are: CGS, CGD, CGB. Now there's one more called overlap capacitance, which is also important. This overlap capacitance has this formula W into L into C. Now COX, remember, is capacitance per unit area, right? So W by L is area, so if you multiply that by capacitance per unit area, you get the total capacitance. That's the logic behind these formulas. So COX is a constant, W and L depend on how the chip is fabricated, And this LOV, the overlap area, is shown here, right? It's where the gate terminal extends slightly over into the above the this N well, the source well, right? Actually, the source is here. Sorry. Oops. Yeah, if I move this over a little bit, you can see the source, I think. Yeah, there you go. So that's the source. Similarly, the overlap length here, LOV, is the overlap of the gate terminal above the well, the N-type well of the drain. So these slight lengths, which is 0.05, 5% to 10% of the total L, right? That comes into this formula for the overlap. Okay, so those are the formulas for the gate capacitances. Then we have the junction capacitances, right? These are also two types, the source to body and the drain to body. The source to body has this formula. It depends on something called SB0, which are some constants. SB0 and DB0 are the values of CSB, CDB at zero body source bias. That means if the body is, if it is grounded, then there is not much there. But generally we know that the body is kept at a negative voltage, right? If that's the case, then you have to apply this formula. And the denominator has VSB by V0. V0 is a junction built-in voltage, which you know from the chapter on semiconductor physics. As soon as you put a N-type and a P-type area, silicon area, doped areas next to each other, a certain voltage naturally happens between the two. That's called the junction built-in voltage, and that tends to be 0.6 to 0.7 volts. So that V0 is in the denominator, but also VSB and VDB. VSB is source to body reverse polarity, and VDB is drain to body reverse polarity. So these voltages generally are given in problems, and then you can calculate CSB and CDB. Now there's something called VDB here, which is generally calculated as two steps, VDS plus VSB. For some reason it's not given by itself, so we end up having to do a VDS plus VSB. That gives you VDB. Okay. All right. So that explains, I hope, the two types of capacitances in a MOSFET. Now, all these capacitors, they have to be added to the model so that we can understand the low, these are the small signal models, right? Not the biasing models, but small signal models. And we are most interested obviously in small signal analysis, because high frequency means high frequency of the small signal applied on the input side. So that's what we are concerned about. Hence we take the original MOSFET model, the hybrid pi model, and add all these capacitances. So that's what you see shown here. So the basic, there are three models we see here, 1, 2, 3. There's a basic model which includes 4 capacitances, CGS, CGD, CSB, CDB. So one of the capacitances, which I think is gate to body, is ignored, and the other 4 GS, GD, SB, DB, they are shown in this model. Now, the simplified model, when the source is connected to the body, This occasionally is used, this type of connection. And if that happens, the source is directly connected to the body, then only three capacitances we have to worry about: CGS, GD and DB. SP becomes 0 pretty much. Further simplification includes two capacitances, CGS and GD, GS and GD. This DB is taken out. And this is because GDB is small enough that we can neglect it. So if you take out these capacitances, this very complex looking circuit becomes a little more simple, and it becomes even simpler, right? But you can see 1, 2, 3, 4 capacitances, here 1, 2, 3, here only 1, 2. Also you'll notice that in this complicated model, the most complex, a new factor called GMB, which is another type of transconductance, has been introduced. Okay, so these are all the models. Another important factor to remember is something called MOSFET unity gain frequency. This is the frequency at which the short circuit gain of the common source configuration drops to unity or 1. So this is a property of the MOSFET. So the higher the value of Ft, the more effective the MOSFET becomes as an amplifier. Usually transistors must be applied at frequencies well below Ft to be useful as amplifiers and oscillators. So based on all that we have studied so far about the internal capacitances, etc., a new term called Ft, unity gain frequency, has been defined. This is the frequency at which the short circuit current gain, which is, so far we have only studied voltage gains, right? We haven't bothered too much about current gains. But that's also an important concept, the output current versus the input current. That has this formula, and this becomes 1 at a certain frequency, and that frequency Ft is the transconductance divided by, of course, 2 pi, but in parentheses here in brackets, CGS and CGD. So this property Ft is a natural property of a MOSFET, and it defines the highest possible value of your frequency of operation. Not necessarily the minus 3 dB cutoff frequency, but the frequency theoretically that the highest you can go in terms of input frequency. You generally have to be well below this frequency. Okay. Now the actual 3 decibel frequency, the minus 3 dB frequency, we'll come to that. There are different formulas and it depends on many other properties such as resistances also. But purely using capacitances of the internal capacitances of the device and the transconductance Gm, you can first come up with a gain frequency Ft. And this is true. All these ideas that we are studying are generally true both for MOSFETs and BJTs. I'm just telling you, in case I don't have too much time for BJT analysis, almost everything we are studying in the same form we apply to BJT also. Okay, so we defined the unity gain frequency Ft. Let's move on to the next slide. Here is a nice summary in table 9.1 in your textbook of everything that we have studied so far on the MOSFET high frequency model. So this is the original hybrid model that I just copied here to show you, and this is the more complex high frequency model. So once your capacitances start appearing, this little thing becomes much more complex, and then all the formulas you require to solve problems. Gm, I told you there's a new GMB which has a complex formula here. And then the rest of it, RO, you know that. Now CGS, CGD, CSB, CDB, the 4 capacitances that we include in the model, they have their individual formulas, it's shown here. FT, the unity gain frequency, also is shown here. So this table is pretty important as we get to looking at problems and so on. Speaking of problems, I have some, so we'll come back and look at these later. Okay, now let's look at the BJT part quickly. Okay, just like we studied for the MOSFET, the BJT also has many capacitances. Whether it's a BJT discretely or a BJT in an IC, you have two important capacitances, C mu and C pi. C mu is here between the collector and the base. C pi is between the base and the emitter. C pi consists of CJE plus CDE. DE is considered the diffusion capacitance. JE is called the junction capacitance. Okay. Now again, we depend on the physics guys to give us all these formulas. So without going too much into detail on BJTs, I've tried to bring everything into one slide. So let's look at the definitions of these capacitances, the formulas, and the small signal high frequency model. Okay, so the gain fall off at high frequencies is caused by the capacitive effects internal to the BJT. There are three types of internal capacitances in the BJT. The base charging or diffusion capacitance, CDE, which has this formula with a tau, and tau is a device constant with the dimension of time, and then IC by Vt, which is Gm. The base emitter junction capacitance, CJE, and we know you add these together, you get the C pi. But this base junction capacitance is twice of something called CJE0, which is like a constant for the device. Then for the collector base junction capacitance, now that depends on certain voltages, and that is what you see here. So the collector to base, we know, is a reverse bias, right, in any BJT. Then there is a constant on top. So the C mu has this formula which is related to the voltages applied. Okay. There's a new term called M, which is a grading coefficient. VOC is the CBG built-in voltage. Okay. Here is the model. Previously we had a simpler model. Now we add these capacitances. There's actually a new term called Rx also that gets introduced. Then finally we have Ft, which is the transition frequency or the unity gain frequency, and that has this formula similar to what we saw for the MOSFET. So this in one slide is a summary of all the BJT stuff similar to what we studied for the MOSFET stuff. Okay. All right. Here is again a table from the textbook, table 9.2, where he gives you the model and he gives you all the necessary formulas. And for comparison, I've just pulled this from some previous slides that we studied. This is the simple hybrid pi model, and this is the high frequency model. Here we are ignoring the capacitances. If you want to consider the capacitances because you are planning to go into high frequencies, then you got to study this model. So what is Rx? Resistor Rx in the model is to model the resistance of the silicon material of the base region between the base terminal B, this terminal, and a fictitious internal or intrinsic base terminal B prime. that is under the emitter region. So apparently you assume that there is a B prime terminal here, and the resistance from here to here is Rx. And this is something that again is given as a constant when we have to solve problems, but this helps to take the B and create a B prime inside and then put the capacitances. Okay? Alright, and all the formulas are here. We got to move on. I have some problems here. As we do these problems, you will get a better understanding of all the constants and the new capacitances, etc. So we'll get some practice using these formulas in the next recording. For now, I have one more important topic to cover, which is 9.3. This will be our last topic in this chapter, and of course the last topic in the course EE3ID. So now that we have studied the device itself, right? Each MOSFET or each BJT has internal capacitances, and we can also model them using the hybrid pi model. But that is only the device itself. Now we have to worry about the rest of the circuit. So what is the rest of the circuit? We obviously take the device shown in the middle in blue. We have a signal source, and we know the signal source will have an internal resistance R signal. There will be a gate resistance for biasing purposes. Similarly, that's on the input side for a CS amplifier. This is a MOSFET amplifier. Similarly, on the output side, you have the drain resistance RD, you have the load resistance RL, right? So once you complete this circuit, you have a real amplifier. That means your input signal gets multiplied by some gain AV, and you get the corresponding output voltage. So now we have a complete amplifier, and how to understand and analyze this. That is the topic for the next 13 minutes, 12 minutes in this lecture. So starting with this drawing, which is figure 9.13, you have the basic amplifier in A. In B, A is the equivalent circuit of the amplifier, the small signal equivalent circuit with the capacitances. Now this is a simplified version, right, because he's showing us only 2 of the 4 capacitances, which is fine. Let's keep it simple. Now the circuit of A is simplified on the input and the output. So what he's done is he's applied some formulas. For example, on the output we have 3 resistances in parallel, so you can create a new resistance called RL prime, which is the parallel of the 3. Similarly, on the input side, he has used a voltage divider formula. Actually, this is a bit of a Thevenin equivalent on this side. So you have one voltage in series with one resistance, so that's a Thevenin equivalent up to this point, right, before the blue stuff. So the values of the Thevenin source, the voltage source is this, and the resistance, Thevenin resistance, is this R signal prime, which is R signal in parallel with Rg. Then the first capacitance and the second capacitance are still there, and your dependent source is still here. Next step, part C, he does some more simplification. Now this CGD, which is connecting the two, this part and this part, he breaks that connection but puts another capacitance called C equivalent. So you have two capacitances now. You have CGS and C equivalent. And the C equivalent is a little bit of a complication, because what it does is it takes the CGD and it gets a multiplier called the Miller multiplier. What is the value of that multiplier in brackets? 1 plus GMRL. Okay. Now remember, GM is the inverse of resistance. So if you take the inverse of resistance and multiply by a resistance, you just get a number. So this 1 plus that number, all it does is it takes the CGD value and multiplies it by some number, say 10 or 20 or 100 or something. Hence it's called the Miller multiplier. So it's almost like this C equivalent is the original capacitance multiplied by some number, 10, 50, whatever. Then the two of them are in parallel, so together they give you C. And you know, parallel capacitors, you just add them, right, to get the equivalent value. So that is a simplified model. And using this, if you plot the actual frequency response plot, it looks like this. And like it tells you here, it's a low pass single time constant circuit. Low pass means the frequency is lower than the cutoff frequency are allowed to pass. That means the amplification happens. The frequency is above the cutoff frequency, and the cutoff frequency here is FH, the high cutoff minus 3 dB frequency. Above that cutoff frequency, the amplifier does not allow the frequencies to pass. That's why we call it a low pass circuit. A low pass allows lower than the cutoff to pass, but higher than the cutoff is not allowed. So that's opposite to the high pass that we saw previously, right? This is a low pass. Okay, one more slide of important information. Now we saw the plot, the frequency response plot. The mid-band gain is flat, right? This portion is a constant. So that portion is the mid-band gain, and it depends only on the resistances and the GM. And this is the formula. The high frequency gain, on the other hand, is a complex value. You can take this AM, this value, divided by this 1 plus S by omega h, or rewrite it as this constant times omega h by S plus omega h. And this form, as I show here, the transfer function is like a low pass STC. STC just means single time constant. So this is a low pass STC network with a 3 dB frequency FH determined by the time constant, whatever is in the R and C here, denominator. This RC, we write it as this: C in R prime sigma. What is C in? It is this GS plus C equivalent, and we saw the C equivalent is this. What is R sigma prime? It's R sigma in parallel with RG on the input side. So that gives you the cutoff frequency in radians or in hertz, and you put that into this and you get the overall transfer function or the high frequency gain at any frequency outside the mid-band gain on the high side. Okay. So this is similar to what we did on the low frequency side, right? What is important is to understand that the transfer function looks like this. The S is only in the denominator, and the actual time constant or the cutoff frequency, which is 1 by time constant. The RC form is still there, but R is a little complicated like this. C is a little complicated like this. Okay. All right. So we have a couple of problems that we'll come back. The very last topic is BJT CE amplifier, common emitter amplifier. The logic is pretty similar to what we just studied. We take the model, which is this portion, right, of the device itself. Actually, this portion, I guess, yeah. RC and RL are external to the device. Similarly, the signal side, the input side, V signal and its source resistance R signal. RB is the biasing resistance on the base, so that is also external. So this is external. Everything else is internal to the device. This can be simplified. So there is a Thevenin equivalent. On the output side, these three resistances are combined to give us one RL prime. There is one capacitance C pi that's still there. C mu will be changed to C equivalent. So C mu is multiplied by another Miller multiplier, and then the internal capacitance, as looking from here or as seen by this source, now becomes Cn as C pi plus C equivalent, where C equivalent is nothing but C mu into 1 plus GMRL prime. The output voltage can be given as minus GM RL prime V pi. V pi is the value here, which has to, we can find V pi, right? V signal is just being dropped here a little bit and the rest is V pi. So that's shown here. So these formulas are similar to what we have seen in the MOSFET case, and if you plot the transfer function, the frequency plot of the BJT amplifier, you see the familiar shape of a low pass filter. So less than the cutoff frequency of FH, you have almost a flat response. Higher than that FH, your response falls rapidly and is probably not very useful. And this cutoff frequency has its formula in the form of 1 by RC, similar to what we saw for the BJT. And the actual formulas to be used are the midband gain, V0 by V signal in the midband has this formula. It's a little more complicated than for the FET, but the form is the same, right? There's a resistances everywhere. There's an RL prime, which is this. The high frequency gain, you take the mid frequency gain, midband gain, and then multiply by this factor. Again, this factor reminds us of a low pass STC network with a 3 dB frequency FH determined by the time constant Cn R prime sigma, which is here, or R prime signal. R prime signal is nothing but R pi in parallel with another resistance. Cin is the sum of C pi plus C mu modified by the Miller multiplier. So these formulas help us solve problems related to the BJT amplifier. Okay, so I've got a couple of problems. We'll look at them in the next recording. So with that, we conclude a very basic introduction to this chapter, chapter 9, frequency response. If you had more time, we could have maybe done a little more because there's many other sections in this chapter, more complicated, but help us understand frequency response even more. But at a minimum, I think if you take this course, you must know everything that I've covered, at least this far in the chapter. Okay? All right, let me stop.